So welcome back guys. So in this one we will be diving much deeper into the concept of logistic regression. So logistic regression is the way to solve binary classification problems where you want to decide between two options. Example, is this a dog or not dog? It's called logistic because it uses special function, the logistic or sigmoid function, which makes predictions. So we will be diving into the whole concept and we will try to understand what the function is and what the whole thing is. So I hope you guys remember the input. So the core concepts behind logistic regressions are input, which are features. These are clues or pieces of information like whiskers, ears, or fur about what you're trying to classify. So in math terms, we call these clues X, which is the list of the numbers. And the second main core concept, this is the list of the numbers, alright. And the second core concept is the weights and the biases. So weights is the thing that decide how important each clue or feature is, and bias is the thing that adjusts the final guess a little something like a starting point. So we have to learn to differentiate both of those things, because in when you are going to program neural networks, then you will be getting to know that this thing, the B will be the perceptron. So that is really important thing for us to remember, guys. So third thing is linear combination. So we have to combine those clues, and when we multiply each clue by its weight and add them up plus bias, that will be the formula that will give us the formula, which will be wx plus b. This gives you number z, which we call the score. And the problem with score is z can be any number, and it can even be a negative number, but we need it to represent the probability and the only number between 0 and 1. So that's where the sigmoid function comes in. So what we try do in this whole thing is we cover the whole thing in the sigmoid function. So that squishes the whole equation into the possibilities of only 0 or 1. So if z is big, then sigmoid will make it close to 1. So we will understand the whole equation now. So I hope you guys understand the whole base terminologies of the basic things. So yeah, given x where y hat equals to probability of y is going to be 1 in estimate of the where x is the input. That will be our base equation, where y hat will be considered as estimate of y, and this thing will be considered as given y equal to 1, given input features as x. So X is a next dimensional vector given that parameters of logistic regression will be W which will be this, and so W is a next dimensional vector together with B, which is just the real number. So given input X and parameters, how do we generate the output? Given input X and parameters W and B, how do we generate output y hat? So that's the questions. Then we get the basic intuition that yeah, this might be the equation we're looking for, just as we mentioned before. The base function were linear combination where to combine clues and multiply each clue by its weight and add them up plus the bias. That's the linear regression equation. So we can try this, but that's what you do if you're doing the linear regression, but this isn't good for binary classification because we want the output to be in the terms of 0 or 1. So in logistic regression, what we are going to do is we are going to have y hat equal to sigmoid W X transpose plus B, and this thing will be considered as Z, where Z will be the sigmoid function. So I'll try to explain what sigmoid function is. So consider this as a Z axis and this will be our 1, and where the curve goes up, that will be the 0.5, and this thing will be really near to 0, so we will approximately assume this is 0. So that's our sigmoid function, and what we are going to do in the whole thing, there are going to be two possibilities with this equation now. So what is going to happen now is we are going to have sigmoid of Z equals 1 upon 1 plus e raised to minus Z. So in this we will be having two situations. So in first situation, this thing will be really big, and that situation will make this thing really close to 0, and the whole thing will be equal to 1, because 1 upon 1 will be equal to 1, and it will be approximately equal to 1 if this is big. If Z will be large. Now the second possibility, when Z will be small, so the whole equation will be like this thing will be really big number, and 1 plus really big number, that means 1 upon really big number, that will equal to approximately 0. So that's what we were hoping to find, guys. So we found our final outputs 1 and 0. So when you implement logistic regression, your job is to try to learn parameter W and B. So y hat becomes good estimate in the chance of y equal to 1. So just for note, when programming neural networks, keep W and B really separate, because B means, I'm correcting myself, I said perceptron in the beginning of video, but B means interceptron. That's what I remember right now. So in some courses these notations are going to be handled differently, but in this one we are going to set up notations in this way, so please follow along, guys. So in some conventions you will be define extra features such as so I'll be writing in different colors, so we are not going to use these features. So in some courses we are going to use features like extra feature x0, which will be equal to 1, and x is going to be nx plus 1, and y is going to be sigmoid of theta gx. So that's what a lot of courses are teaching, but that's not what we are going to use in our course. So it will be looking like this: 1, theta 2, and theta nx. So this will be our B interceptron when we develop neural networks, and all these things will be our W. And it will be clear as we are going to work on the neural networks, we are going to develop the whole code, so don't worry about this, it will get clear. So we'll not use these things which are written in the red in our course right now. So yeah, I hope you guys understood the concept of logistic regression, and I hope you guys are healthy and keep writing and keep being legendary. Peace out.